Hi folks. Now in this video we're going to look at a couple of examples of using multiple regression to answer some interesting real-world questions. And as a case study we're going to use this running example on house prices from Saratoga County, New York. The goal here is to show how, together with multiple regression, this data set can be used to address some interesting facts about the market for houses in that area, the kind of things that might be relevant to anyone who is buying, selling, or filing a tax protest for a house in that area. And let's start by looking at this plot right here. This is a plot showing the relationship for every house in Saratoga County, New York that's on the real estate market, the relationship between price as the Y variable and number of fireplaces as the X variable. And this is the kind of plot that you might look at to naively answer the question, how much is a fireplace worth? You can imagine, knocking in a wall of your house and building a fireplace, and how much would that improve the taxable value of your house? Well, the naive answer that you get from running regression of price versus number of fireplaces is estimated by this equation right here. And you notice the coefficient on fireplaces is about $66,700. So the interpretation of that is that for every extra fireplace you add, from 0 to 1, from 1 to 2, and so forth, you improve the value of your house on average by about $66,700. That's the kind of thing that might be of interest to a tax assessor. If you were to modify your house to add a fireplace, the tax appraiser in that area would then come in and say, all right, clearly you've changed the value of your house by adding this nice feature, this fireplace, and this regression equation would support the argument that your house just went up in value by $66,000. But hang on a minute. There's an issue here, and the issue here is confounding. If we look at the relationship between fireplaces and some other variables, let's take two, like living area of the house as measured in square foot, and the lot size of the house is measured in acres, here plotted on a log scale. What you'll notice is that more houses with more fireplaces tend to be bigger on average. There's a clear relationship, an upward relationship between the number of fireplaces and living area. And they also tend to be on houses that have bigger lots. There's an upward relationship right there. And of course, those are two features that are very obviously going to affect the price of a house. Bigger houses here tend to cost more here, and houses that are on bigger lots also tend to cost more because of the intrinsic value of the property they sit on. So this motivates the question. When we see that houses with more fireplaces, one extra fireplace on average improves the value of a property by $66,000, is that because of the fireplace, or is that because those houses that have extra fireplaces also tend to be bigger and to sit on extra lots? This is confounding. In other words, there's a competing explanation, a couple of other variables here that are correlated with both the predictor, number of fireplaces, as these two plots show right here, and also the response, price, as these two plots show right here. And anything that's correlated simultaneously with both our predictor and our response is called a confounder. Let's clear some annotations here. Okay. So, how do we handle this? Well, we know that what multiple regression does. Multiple regression allows us to estimate a partial relationship. In other words, the rate of change between the Y variable, in this case price, and the X variable of interest, in this case number of fireplaces, holding other variables constant. And if we estimate a multiple regression relationship here, with price as the Y variable, and then three variables in the X side of the equation, square footage, acreage, and number of fireplaces, what you'll notice is that we get a much smaller coefficient on fireplaces. Before, we were saying that each extra fireplace was worth $66,700. That was the overall relationship, but the overall relationship was subject to confounding, at the very least due to square footage of the house and size of the lot. And once we adjust for those confounding relationships, fit a multiple regression model to hold those constant and get the partial relationship between fireplaces and price, we see that it's a lot smaller. And so this example emphasizes the nice use of multiple regression to adjust statistically for the effect of confounders of a relationship between a variable of interest, like fireplaces, and a responsive interest like price. This is one of the most useful real-world applications of regression modeling, and we'll see it in many, many other similar examples. So in general, we'll complicate this later, but the advice is, if you want to estimate a partial relationship, make sure you include the appropriate confounding variables as context for that partial relationship. Of course, we're not done here. We had an estimate for the fireplace coefficient of a little around $9,000, but of course we have some uncertainty associated with that coefficient as well. And a very straightforward way to characterize that uncertainty, as we've learned, is to bootstrap the regression model. That is, to repeatedly sample with replacement from our original sample to mimic the variability that we would get if taking real samples from the real population, and for each of those bootstrap samples to refit the model. So if we do that, we get a sampling distribution of estimates of the partial slopes in our regression model. And what you're looking at here is the sampling distribution using bootstrapping of the fireplace partial slope on the left and the square footage partial slope here on the right. And so if you want to interpret this histogram here as giving you some notion of uncertainty about the value of a fireplace, well, let's make a confidence interval just by I here. Maybe that's about a 95% confidence interval. So this is probably like, $2,000 to about $17,000 for one fireplace. Okay? And the key thing is this is holding lot size and square footage constant. So we always want to make sure we quantify uncertainty in regression models and don't just leave it as a point estimate, but actually give some kind of confidence interval for our estimates. The other thing that we want to do is make sure that we check the assumptions of our model before we put too much faith in their conclusions. And we remember that an important assumption here is linearity, that the response varies linearly with the predictors. And there's a couple of ways to check the assumption of linearity in a multiple regression model. The sort of more careful but more tedious way is to plot the residuals, and here on the left-hand side as an example, plot the residuals versus each of the individual predictors in our regression model. So in this case, that would be fireplaces, lot size, and square footage of the house. This plot on the left-hand side of this panel shows a plot of the model's residuals versus the number of fireplaces. And what we would hope to see is no systematic pattern. And indeed, we don't see a systematic pattern. We notice that the residuals are pretty much on average 0 for 0 fireplaces, 1 fireplace, 2 fireplaces, 3 fireplaces, etc. The one where the residuals look a lot different from 0 on average is for 4 fireplaces. But what you should notice here is that there's only 2 houses. Okay, so that's probably just extra noise, and that's not really something to worry about to sort of chase a major nonlinear fit to try to get a better residual fit for only those 2 houses out there. And maybe we should just acknowledge that our model is going to be pretty good for houses between 0 and 3 fireplaces, but maybe not so good for all of the mega mansions with 4 fireplaces. That's fair enough. And of course, we could do this same plot, not just versus fireplaces, but also another plot versus square footage, versus lot size, and if we have other predictors in our model versus those two, and looking for violations of the linearity assumption in each of those plots individually. Another kind of, it's a slightly rougher picture, coarser picture, but it's a lot simpler to fit and get the picture easily, is to plot the residuals not versus each predictor variable individually, but versus the composite sketch of the y variable given by the fitted values. That's y hat. So this is a plot of the residuals E versus y hat in the regression model. And what we should be looking for here is a straight line fit, no systematic variation, or I'm sorry, this is actually, let me back up here. This plot over here is actually a plot not of E versus residuals, but y versus y hat. And that's a fine thing to do as well. And what you should be looking for is a straight line, which is exactly what you see, the assumption of linearity right here. And you should be looking for no systematic pattern. That is areas where some residuals are, say, way above the line on average, and areas where other residuals are, say, way below the line on average. We don't see any of those pathologies here, and so for this particular fit, we're probably happy with the assumption of linearity. What would you expect to see if you didn't see a good fit? Well, this would hark back to the unit on nonlinear curve fitting, if we saw nonlinearity and say we plotted the residuals versus x here, and we noticed that there were some areas, say, where most of the residuals were above, another area where most of the residuals were below, and then another area where most of the residuals were above yet again, that's a textbook example of a nonlinear fit that calls for some kind of transformation or addition of a polynomial term to handle it. So this picture here looks like healthy, nice and linear residuals. This plot here looks like an unhealthy residual plot that calls for some kind of modification to the assumption of linearity, be it changing the transformation or adding polynomial terms to capture those nonlinear trends. Okay. So let's go for another example right here to just show how we can use multiple regression to answer interesting questions, and this will also give you an idea of how we can use grouping variables in multiple regression. And we'll address the question of how much gas heating is worth in Saratoga, New York. Saratoga is pretty cold. The average January day has a low of 13 degrees Fahrenheit. That's pretty far below freezing, and a high is even below freezing. That's 31 degrees Fahrenheit. So heating your house is a big deal. And the cost of different heating system types, you can imagine, very easily influencing the desirability of that house on the market. And if you look, for example, at heating system type, whether it's gas, electric, or fuel oil, the kind of system where a big truck comes and delivers heating oil for the winter, and you use that to heat your house out of the tank below your house, you notice some systematic differences here. The gas-heated houses tend to be higher on average. The electric heated houses tend to be lower on average, and the fuel oil houses tend to be somewhere in the middle. So there's some clear differences in terms of average sales price for houses with different heating system types. And the question is, how much is gas heating worth? Well, if we just compute the group means, the mean price of houses with gas heaters is about $228,000. Versus, say, electric, which is $165,000. So you might naively conclude that the difference between gas heaters and electric would be $228,000 minus $165,000. And what is that? That's, about 35, I don't know, that's something like, what is that? 50, it's about 65, something like that. Okay, just doing the mental math. So that you might conclude that it's about a $65,000 premium. Okay, and that would be naive, right? And the reason that's a naive answer is because it's just the overall relationship between heating system type and price. It's not holding any of the other features of the house constant. Maybe the bigger houses tend to have gas heaters, or the newer houses tend to have gas heaters more frequently than the small or the older houses. These could easily be confounding variables. So let's remember, if you want to isolate a partial relationship, you have to include potential confounders in the model. And so we'll do this here by including two sets of terms. First of all, there will be dummy variables for heating system type, fuel oil, electric, etc., treating gas as the baseline to model the partial relationship of interest. And then we're also going to include all of the other possible confounding variables that we had in our previous regression equation, which had living area, lot size, and the number of fireplaces. If you want to write out the equation in terms of the partial slopes and the dummy variable coefficients, it's right here. And you notice gas is the baseline. I don't see a dummy variable here for gas heating, only for electric and oil heating. And these coefficients are both negative right here, suggesting that the premium for gas versus electric heating, instead of like $65,000, looks to be about $14,000 right here, based on this dummy variable coefficient right here, adjusting for confounders. And that's a key thing. And what confounders are we adjusting for? Well, they're whatever else appears in the regression equation: square footage, lot size, and number of fireplaces. And if you want to summarize these coefficients in a nice little table right here, that's what we've done up in the top here. You've got the estimate, the bootstrap standard error, and the 2.5 and 97.5 percentiles of the sampling distribution calculated by bootstrapping, which give you the endpoints of a 95% confidence interval. Okay, so there we're seeing several things together. We're seeing the use of multiple regression to isolate a partial relationship, as well as the use of bootstrapping to quantify our uncertainty about the coefficients in that model, which is to say, give a range of plausible values for some partial slope of interest, like in this case, the dummy variable coefficients on heating system type. Finally, a question that often comes up when we're talking about multiple regression is to ask whether some particular term is statistically significant at a specified level, like 5%. And all statistically significant means in this context is whether 0 is a plausible value for that partial slope in the multiple regression model. Remember, a coefficient of 0 means no partial relationship between the response and the predictor once we adjust for the other terms in the model. And so when we say that a predictor is statistically significant, all that we mean is that we think it has some non-zero partial relationship with the response. Now, we're going to take up this question of assessing statistical significance a lot more in the chapters to come, but I'll give you a few quick observations and guidelines here. First, and this is a bit counterintuitive at first, we usually express the statistical significance level as the opposite of the confidence level. Okay, so if you have your confidence level is 95%, what does that imply? That implies that your statistical significance level is 5%. Where a confidence level of 99% would imply a significance level of 1%. That's a little confusing at first, but just remember, the lower the significance level, the stronger the evidence that some variable has a non-zero relationship with the response. Second, in multiple regression models, we can often, in many cases, just assess statistical significance by looking at whether 0 is included in the confidence interval. And the reason is that all that statistically significant means is that 0 is not a plausible value. And because a confidence interval is giving us a range of plausible values, we can just read off directly whether 0 is in the interval. So let's take two 95% confidence intervals for the terms in this table back up here, and let me erase all of the associated gunk up here. Let's focus first, for example, on the coefficient for fireplaces right here. Okay, so our 95% confidence interval is like 980 to 14,000, roughly. And 0 is not in this interval. So this interval does not contain 0. That is a 95% confidence interval. Therefore, we would say that fireplaces is significant at the 5% level. Right? Because it's a 95% confidence interval, and significance is 1 minus the confidence interval. Simple enough. So we are at a 5% significance level, ruling out 0 as a plausible value for the partial slope between fireplaces and the response. Let's try a different example. Let's look, for example, at the coefficient on lot size, right here. Okay, so here, the coefficient on log of lot size, the 95% confidence interval goes from minus 1047 to 6457. And that means 0 is in this interval. Okay, and all that means is that we can't rule out 0 as a plausible value, and so we would say that lot size is not statistically significant at the 5% level. Okay? Now, all we're saying when we say it's not significant is that we can't rule out 0 as a plausible value. But what I want to point out here is that there's a lot of other values that we can't rule out either. For example, 6400 is also in here. Is also in this interval right here, right? Because the interval goes up to 6457 on the top end. So that means we can't rule out 6400 as a value of the partial slope either. And so this is why kind of worrying too much about statistical significance often isn't very responsive to the requirements of some particular data analysis problem. In general, the confidence interval spans the range of plausible values, and that is a lot more informative than the question of whether something is statistically significant. Remember, something can be non-zero, and we can be very confident that it's non-zero, but it can still be very small. Similarly, we can not be sure that 0 can be ruled out. In other words, something can fail to be statistically significant, But it could also still be consistent, the data that is, could also still be consistent with the idea that a partial slope is very large, exactly in this context, because it could be 6,400, which is kind of a big number. So my general advice here is to focus in most situations on thinking about the confidence interval rather than the statistical significance. A lack of statistical significance really could just mean a big standard error. In other words, that we have a lot of uncertainty about the magnitude of some variable's partial relationship with the response. It doesn't necessarily mean that the variable is small, and it doesn't prove beyond a shadow of a doubt that that variable is zero. Okay? Another way of saying this is that an insignificant coefficient means that we have an absence of compelling evidence for a non-zero partial slope, but it does not mean that we have found compelling evidence that the effect is absent. So absence of evidence versus evidence of absence are different things, and statistical significance means absence of evidence. All right, one last topic here, and that's about getting prediction intervals from multiple regression models. And this is really, really simple. It goes exactly the same thing as we did before. So let's say that we built a predictive model, including all of these coefficients, all of these variables in this model right here for house prices in Saratoga, New York. We've got bedrooms, bathrooms, living area, lot size, fireplaces, fuel system type, and then whether a house has central air conditioning, and then finally the age of the house. And we've estimated coefficients in that multiple regression model using ordinary least squares. How do we make a prediction? Well, it's simple. If we have some new variable x star, okay, and here x star is the particular combination of all the x's for your new house. Okay, so it's not just one x, it's a new house that has a particular combination of bedrooms, bathrooms, living area, lot size, fireplaces, fuel system type, central air, and age. All of those variables at once, that's x star right here. And there's, if you want to write that mathematically, we're saying that x star is like x1 star, x2 star, all the way out to xp star, since there are p predictor variables in the model. And to form a prediction interval, it's a very simple two-step process. First, form your best guess, that's your y hat, and then go plus or minus some multiple of the residual standard deviation to reflect your uncertainty, exactly as you did in the first unit when we were talking about prediction intervals from one variable regression models. So nothing changes, and if you look in this picture up here, what you can see is a 95% prediction interval for a house that has a predicted price of $257,400. That's our predicted price, and if we go up roughly two residual standard deviations, we get a 95% prediction interval for the actual price. Okay, so we've covered a lot in this chapter, but that should give you a good feeling for how you use multiple regression to answer interesting real-world questions.